Okay, now the form in which I have this is the form in which you would integrate it with respect to your parameter. Okay? And you ask about whether we use a unit normal or a unit tangent or whatever. It depends on whether you have a dt here or a ds. Okay? And ordinarily, when you do a flux integral or a line integral of a vector field, okay, you're not going to do it in terms of distances, but the magnitude of this vector times dt is your distance, right? Okay, so I could write, for example, on this one, x prime I plus y prime j dt is a ds vector. Okay? dt is how much your parameter changes, and that's how much it causes the x and y components to change. Okay? And that, of course, ds is the magnitude of ds, right? Which is the square root of x prime squared plus y prime squared dt, which is what you're used to using when you do an integral of a scalar function where you don't have a dot product or anything like that. Okay? So this is how it relates. So this is like I can write this. Okay? T is your unit tangent, x prime I plus y prime j by the magnitude thereof, right? So now you have a unit tangent, which you multiply by your ds, which is this, right? Clearly, when you multiply this by this, the square root of x prime squared plus y prime squared divides out, and you end up with this. Now, that's something you want to look at and sort out, okay? In a context of doing some integrals, you can understand how all that works. Similarly, your unit normal could be written as y prime I plus x prime j over the square root of x prime squared plus y prime squared, right? And then you'd have to multiply that by a ds, right, which is the square root of x prime squared plus y prime squared dt. Same thing. Same expressions. Okay? So you do want to sort that out. But so what I was about to say, and I really kind of almost don't have time to say it, but I'm going to say it anyway, is Green's theorem written in this format.